So lesson 29, power versus resistance. We will learn how power and resistance are linked. Um, this is sort of loosely based off the idea that I've just talked to you guys about resistance. I've just talked to you guys about power, but I want to know how these two formulas linked. We've already talked about the power formula way back. If I go backwards to all the way when we talked about power, we talked about power here. And we said the power, we found a formula for calculate the energy. The energy is equal to, pardon me, the energy is equal to E equals VIT. Okay, it's only two quick ideas, so it shouldn't take too long anyway. We start off by learning, there we go, it works. E equals VIT. We learned that at the start. The energy is equal to the voltage times the current times the time. The reason we knew that is because the voltage is how much energy per coulomb. The current is how much coulombs per second, and then we multiply it by second. So essentially we're asking how much energy does each coulomb have, how much have we got going through, and how much time have we got to do it. That led us to working out, well, we can actually work out this idea of power. Power equals VI. We said that power equals VI because we know that the more power we've got going through a circuit, the power going through a circuit is equal to the amount of voltage that circuit has multiplied by its current. And so it gives us like energy per second. So some things with lots of power need a lot of energy per second. So something like, as I said to you guys, believe it or not, a toaster is a very high power and a kettle are high power devices. But it doesn't matter because they're not on all the time. A fridge is actually a low power device, even though it's on all the time. Some of the ones that are bad are like TVs. TVs are high power and they're on for long periods of time. So that's one of the reasons why we've got to be careful. Now, after we did that, we talked about Ohm's law. Ohm's law essentially being V equals IR. We know that the voltage, the amount of energy that can be delivered, is proportional to how quickly it can move versus how much stuff is slowing it down. Today, what I want to do briefly for a very short lesson is combine these three formula. I'm going to do that in two ways. First, I'm going to take this formula here, P equals VI. Now, I already know that I can rearrange this formula for V or for I. Let's arrange it for V first. So if it's already arranged for V, I could replace this V up here. I'm going to write substitute V equals IR. Let me show you what happens. I'm going to write down P equals, but instead of V, I'm going to write down IR. IR. And that's multiplied by I at the end. Okay, does everyone see what I sort of did there? How I went from V, how I substituted this into where V is? Does that make sense? Does someone say yes on the chat or no or like or yep, okay, cool. I heard a brief yes because I've got my volume turned down a fair bit, so let's turn that up. Okay, so yeah, cool, thanks. So the next step here is just to say, all right, well, if I know that I've got an I here and an I here, what I've got essentially is got I times R times I. So the final formula is P equals I squared R. And that is a formula that we sometimes use when we talk about power. This is sometimes known as the power, and you guys will learn this, we might use this later on. This is called the power loss formula. And the reason it's called the power loss formula is because it usually gets used to calculate if I have, like high voltage lines, and they're running, you know, like this, the amount of power that gets lost from those high voltage lines is going to be proportional to the current, how much current you're pushing through them versus how much resistance. And it's actually going to be really dependent on the current, because it's I squared, not just I. So what we actually do is we usually, believe it or not, this might sound really weird, with these lines, we don't use high current. We actually use high voltage instead. If you look at V times I, if I want to get a lot of power from one point, point A to point B, I want to get a lot of power from here to here, I'm going to use, and I need to get either a high voltage or a high current. And it actually works better to use a high voltage. That's why they call them high voltage wires, because they've got a high voltage, not a high current, because high current will lose power quickly. Now, I promised you guys 2 formulas today, and I've only given you 1, so it's time for the second formula. The second formula is, we're going to do the same thing. We're going to do P equals VI. But this time, instead of replacing the V, we're going to replace the I. So we're going to change this formula down here to look like this. V divided by R equals I. So that means that if I take this and I substitute I equals V on R, I will get this formula. P equals V times the I is going to be replaced with V on R, which is going to be V times V over R, or V squared on R. And that is another form of the power formula. So ultimately, we've ended up with 2 formulas. And these formulas, I'm hesitant to say that they're new, because in all honesty, right, these 2 formulas are not new. You guys could have come up with these formulas pretty easily, because, you know, you guys now know these 3 formulas. So you guys could have probably come up with those formulas. I told you, I want you to make a formula with power, current, and resistance. And you guys probably could have figured out, oh, I could substitute that in. And sometimes making formulas that are completely new is useful. Sometimes it's not, but sometimes it is. You guys should be able to look at the energy formula and think, I could do something similar with that energy formula. You could make I squared, you know, I squared RT or something like that, you know. That's how much energy is released during a certain amount of time, but we're not going to go through that in too much detail. My point that I'm trying to make is these are 2 new formula that I want you guys to have in the back of your head when we're dealing with these problems. Now, what we're going to do together now is we're going to have a look at 2 problems, and we're going to see how these formulas can be used. Now, again, I would show you these on the Google, on the PowerPoint, but my PowerPoint's having some challenges at the moment. So let's just open up. Are there any questions before I close this actually? Are there any questions, queries, problems? If not, I'm going to jump over to here. Now this is in your textbook. Okay, so what we're going to do is we're going to look at 2 of the work, and here we've got the formulas that I just talked to you guys about. Okay, here are the 3 power formulas. Now and this is just, yeah, pretty much what I'm working on. I'm going to go through these two worked examples with you guys, and then we're going to pretty much, that'll be the end of the lesson. So give me a second. I'm doing that because, yeah, sure. You know what? If you want to just read what they've said, how they do the problem, then you can. But we're going to try and do it ourselves, just so that you guys can see how this would get done. So a portable radio has a total resistance of 18 ohms and 6 volts, consisting of 4 1.4 volt batteries in series. At what rate does the radio transform electrical energy? So at what rate are we turning, are we actually pumping electricity? The first thing to note here is this is actually not really that important. I don't think it's that important, because essentially what they're saying is they've got all these batteries, all these cells are in series. I should point that out at some point. When I talk about batteries, I will. But one cell is called a cell. When you put 4 of them in series, you end up with a battery. So a battery is actually not just a thing that you call a power supply. A battery is actually a couple of cells put together. Now, if you go 4 times 1.5, that's going to equal 6 volts. And you know that because they're in series, you can just add them together. If they were in parallel, you would have less voltage, but you'd end up with more current. So, but we'll talk about that later on. Let's talk about these bad boys here. So in this case, we want to know at what rate the radio transforms energy. Well, we're looking for the rate of energy transfer. We're looking for power. In that case, power is going to be, well, we need to use one of our 2 formulas. We've got the voltage, we've got resistance, so it makes sense to use V squared on R. V squared is going to be 6 squared divided by 18, which is going to be 36 divided by 18. Look at that, I can do that in my head. That's going to be 2 watts. Well, it's going to be 2, and then I know because we're talking about power, the symbol is watts. So that's how I would solve a problem like that. Oh yeah, sorry, you are completely right. Quickly pointed out to me that 6 times 1.5 is not 6 volts. I should have said 4 because it's 4 1.5 volt. That's how you get 6 volts. Sorry about that. So that's how you would use this formula. The first thing I guess the hardest part, in my personal opinion, to identify this formula, to identify this question, is to read this and see when it says, at what rate does power transform electrical energy? When you see at what rate, that is a very complicated way of saying what is the power, because power is the rate of energy transfer. So power is energy per second. That's why it's called the rate of energy transfer over time. So that's how you do this question. Are there any problems, queries that you guys don't like about this? Yes, no? Okay, I'm gonna move on. Yep, look at that, 2 watts, I got the correct answer. I'm a genius. Well, you guys are geniuses too now that you know how to use the equation. So clear all, let's go down to the next one. And we'll do this one really quick. And then that's going to be the end of the lesson. So let's go with white this time. And yeah, and again, this is pretty lazy. As a teacher, I consider this pretty lazy. I should have rewritten these in PowerPoint and had these ready for you guys. But of course, I've been having some issues. The pop-up toaster is labeled 240 volts at 800 watts. Okay, cool. So what? What is the normal operating current of the toaster? Okay, current. Okay, so they've given us power and they've given us voltage. They want to know the current. Well, we can do that pretty easy. power equals, well, we're going to choose, they've given us voltage and they want current. So we're going to use this formula. The reason we use that formula is because it's got voltage and current in it. Okay. So when I then go, the current, if I divide both sides by V, the current is going to equal the power divided by the voltage. We know that we've got 800 watts at 240 volts. So that's going to give us the average running thing. I'm going to grab my calculator. 800 divided by 240 volt is 3.33 recurring amps. Yeah. So let's, I'm going to be honest with you, the amount of decimal places doesn't matter too much. I'm just going to go 3.33 amps. I always like using 2 decimal places. It's just sort of, you know, that's just sort of the standard convention is 2 decimal places. And no, I'm not going to do 3 1/3 because honestly, the problem in physics is we don't usually use halves and thirds and quarters and stuff. We just write things down as approximations. And I know for some of you guys that are doing methods or pure maths or specialists, like, oh, what do you mean you write down things as like approximations? It's like, yeah, I know it's not accurate, but in physics and engineering, you don't need to know like infinite accuracy, like square root 2. You just have to be able to write 1.4 and stuff like that. Okay, B. What is the total resistance of the toaster while it is operating? Okay, total resistance. Now, there are 2 ways we can do this problem. Let's do this first the way that the question wants us to do it, given that if they've given us the power and the voltage, we can use the formula P equals V squared on R. Now, we can then go, well, if I swap these two, PR equals V squared, R equals V squared divided by P, which is going to be 240 squared divided by 800. That's going to give us 240 squared divided by 800. It's finding a bit weird that there haven't been any I squared R questions, but that's okay. 72. Normally what I would have done if I had planned this better is I would have given you an I squared R question. 72, we're finding resistance, so that means this is ohms. That's one way to do the answer. Now there's another way. The other way that you could maybe do the answer if you really wanted to, you could say, well, you know, R equals V over I, because V equals IR. We already know V is 240 volts, and now we know that I is 3.33 amps. So if I do 240 divided by 3.33, I get 72. So there's 2 ways to solve the problem. Now, some of you might say, well, which way is the best? And you know what? Usually I would say there's no best way to solve a problem. It doesn't matter as long as you get the correct answer. Except in this circumstance, this way is the better way. Well, how can you tell? The reason this way is better is because this method on the right uses this. And I'm going to point this out because I do this pretty much with all my classes. You will notice that that 3.33 comes from a previous answer. Okay? All right. That doesn't make a difference. What if I had made a mistake? What if when I did this question here, it came out to be, I put it into my calculator and for some reason it didn't come out to be 3.3. It came out to be, I don't know, let's go with 3.2. Because maybe I put in 250. If I had have gotten 3.2 instead, and then I used that answer here, I would have got an even worse answer here. I would have carried my error over from one place to another. And so I wouldn't have just got one question wrong, I would have got 2 questions wrong. If you notice this example down the bottom, we use only the results that we had in the question. We use the 240 and the 800. That's exactly what they gave us in the question. We're not introducing anything new. So even if we had completely stuffed up this first question and got 3.2, we still would have got this question on the bottom right. And that's the difference. Also, because this method exists, if you did make a mistake and you used 3.2 here, you probably wouldn't have gotten consequential marks, or at least you wouldn't have gotten full consequential marks, because they would have said, well, you could have used this method and gotten the right answer, so you made 2 mistakes here. So just keep that in mind when you're doing problems, is that you want to avoid, if you can, and this isn't always possible because some type of extended answer questions you have to, but you want to avoid using results that you've already come up with. It's the same way whenever I teach students how to work out stuff with trigonometry. I go to them, okay, cool. Let's just say I tell you this is 30, and then this is 20 degrees, and then they find out what this side is. And they go, cool. And now I want you to find out this side. And then they go, oh, well, we'll just use this side here. I'm like, no, don't do that. Because if you made a mistake working out this side, you carry that mistake over. Keep using this. So in this case, you would use, I know this is off topic, you would use sine and you would use cos. I've had students say, oh, use sine and then use tan because we've got opposite. I'm like, no, don't do that. But that's a different sort of point. Ladies and gents, are there any questions about what I've done down the bottom here? Any queries? Anyone like, well, that's completely new, I've never seen that before? If not, there's no new homework. It's just going to be finishing up 3.6, which is, if I go, oh, there is a question. Is there a question? Can we have more practice problems? I mean, more practice. So when you say more practice problems, as in more practice problems of this type or what? Okay, you want another practice problem this time. Let's grab a look then. We'll see what we can do. I'm going to clear all these drawings. I'm going to quickly, and so you can see here that they got this 3.3, and then they also got 72. So they got the same sort of results. After that, you directly jump into the next bit. Well, there is one more problem here, which is very, very similar. So I might as well do that really quickly. Ladies and gents, I'm pretty much done. I've got about like 4 minutes left. If you guys want to wrap up now, you want to leave, then that's up to you. You guys now know that your homework is to do 3.6. And I've set some questions for that. I haven't set all of them because we're going to look at this. This is all about this color codes, which I hated so much. You don't have to worry about that one. The last question is a bit complicated and deals with temperature logarithm scales. And I know that you guys could do this question, but I'm like, I'm not going to get you worried. I'm not going to hassle you with it. So don't worry about question 9. But all the rest of them, I want you guys to take a go at. If you guys want to leave, you can, but I'm going to go through one last question. I'm going to go through this practice problem at the bottom here. It's very similar to the last question. So if you don't want to stick around, I understand. Rochung, I'm doing this for you, boy, so you better be paying attention. Also, Rochung, completely separately, you need to make sure that you have done that financial maths test. I'm still waiting for that from you. And I can't give back the other students' marks until I've got yours. A microwave oven is labeled at 240 volts at 600 watts. Okay, so we've got a voltage here and we've got a wattage, we've got a power here. Right, what is the normal operating current? Okay, so we need, and it's pretty much exactly the same. The idea is a practice problem. We need a formula that has current in it. We need a formula which is current, power, and voltage. That's going to be P equals VI. So therefore, I'm going to use, and I want to know the current, so P divided by V equals I. What's my power? My power is 600 watts. What's my voltage? My voltage is 240. So that's going to give me my current. 600 divided by 240. That gives me 2.5 amps. Okay, that's 2.5 amps. And then what we'll do is we'll go, well, what is the total resistance of the microwave oven when it is operating? Total resistance, P equals I squared. Whoopsies, what am I doing? Wrong one. Oh, crap. Crap. There we go. I'm going to do not that. I'm also not going to erase it because that gets rid of it. I'm going to say, well, I've got V and I've got P. Is there a way that I can calculate R? And there is. I could use P equals V squared on R. So therefore, R equals V squared on P. V was 240 volts, 240 squared. And the power was 600. 240 squared divided by 600 is going to give you 96 ohms. That's going to be the resistance. Now, you will see that there are problems like this all the way through here. There should be some problems like that down here, at least. If we go have a look, question 5, at what rate is thermal energy transferred to a wire 5 ohms carrying 0.3 amps? So P, so they're giving you a resistance and a current. They're giving you resistance and current. You should remember, okay, which one of these has resistance and current? Well, look at that. If I know power equals I squared R, so that's where you would use I squared R. If you know that you've got 0.3 amps, 0.3 squared times your resistance, which is 5, then that will give you guys the answer to that one. So, and then down here, we've got pretty much the same formula as before. So we've got one question with I squared R, and then this question here looks like it's another one similar to these ones above. So yeah, this looks like there's only one question with I squared R in it, which is question 5. Maybe question 4 has got I squared R as well. I'd have to look. But that's sort of, yeah, maybe question 4 has got it as well. But that's sort of how you do it. I want you guys to work on that. Friday will be a little bit more organized. Sorry about today's lesson, but hopefully you got something useful out of it.